This video is sponsored by PCBWay. Hello there and welcome back to another video. In today's video, I've got two broken mini PCs that were very kindly sent to me by fellow YouTuber Carey Holzman. So first off, thank you Carey for making this video possible. Carey reached out to me and offered to send these computers over for repair, as he'd tried to fix them before and was unable to get them working. So let's see if we can get these systems working. I'm going to start out with this one, which is a B-Link EQ12 mini PC that has an Intel N100 CPU, 16GB of DDR5 RAM, and a 500GB NVMe SSD. After getting the computer out of the box and plugging in both HDMI and power, I pressed the power button which illuminated and the fan spun up. However, there was no display on the monitor even after a while. Carey told me that this computer had its RAM switched out, and after that it never posted again even after reinstalling the original RAM. So, with the problem confirmed, let's start digging around inside this computer to see what's causing it to not post. After removing several screws and two plastic panels, I was granted access to the motherboard where the RAM and SSD are both conveniently positioned on the top side. It looks like this system is loaded out with a 16GB stick of Crucial brand DDR5 4800 RAM, which isn't too shabby. If all else fails, hopefully that memory stick is still good and I can salvage it. Carey went through the standard troubleshooting steps with a system that's exhibiting this problem, as he's a very experienced computer technician, but I'm going to go through the basic troubleshooting steps that one should do when met with a power but no post or display issue for those of you who may want to learn these steps. I took the RAM out and put it back into its slot, which in turn reseats it. I then tried to power on the system again, but there was still no display. Now, if the system had more than one RAM slot, I would have tried the DIMM in all of the different slots to see if the issue revolved a dead memory slot or channel. However, the Intel N100 only has one RAM channel, and this B-Link computer only has one slot on that channel, so I can't do that here. I also don't have any other systems that use SODIMM DDR5 on hand, and somewhat for that reason, I don't have any spare SODIMM DDR5 modules that I know work. So, for the time being, we're going to have to assume this RAM stick is fine. I also know that Carey tried a couple different RAM modules when he was diagnosing this computer, and none of them worked. So presuming this RAM stick to at least not be the primary source of the issue doesn't seem too crazy to me. I'll provide links to the videos that Carey did on these computers in the description so that you can see what he tried out on them in full detail. I then went ahead and removed all of the other parts of the computer, such as the M.2 drive, Wi-Fi card, and the RAM just for now. I then removed the motherboard from the case and started to look at it to see if there was any noticeable damage to any part of the PCB, but it didn't seem like there was. I also went ahead and located the CMOS battery so that I could test whether or not it was dead. It is possible that the CMOS battery was faulty, and when the RAM was switched out, it coincidentally finally failed, which is causing this no-post situation. These battery terminals are really tiny and quite hard to work with, so sadly I can't use my custom CMOS battery tester. Instead, I grabbed my multimeter, and with some superfine probes, I was able to get a reading on the battery's voltage, which is completely good at about 3.05 volts. With the CMOS battery known to be good, I left it unplugged from the board for a little while longer to hopefully give the BIOS more of a chance to clear. In that time, I chose to go ahead and pull off the CPU cooler for the sake of inspecting the board underneath it, and double checking the thermal paste application. Thermal paste shouldn't be causing this issue with the known circumstance, but why not give it a check while investigating the components hidden under the heatsink. Additionally, the Intel N100 in this system is soldered to the motherboard, so a CPU reseat isn't something we can try. If it was a regular desktop system with a socketed CPU, that's another thing that I would have given a shot. I pulled off the heatsink by unscrewing its mounting screws in a cross pattern, which is extra important in this situation because this cooler is direct die. It would be much easier to crack the die by unscrewing it unevenly because it's a direct die cooler, so always be careful when dealing with these kinds of heatsinks. Under the cooler, nothing seemed out of the ordinary, which was mostly to be expected. I applied new paste, remounted the cooler assembly, plugged our CMOS battery back in, and reinserted the DIMM. I then decided to try powering on the system once more, this time with only the bare minimum necessary components on the board. I also powered it up outside of the case, just being careful not to let anything short out while doing so. Once more, we had a power light and I could hear the fan spinning on the bottom, but there was no display. I was still pretty unsure of what could be going on here at this time, so I went ahead and decided to give the power adapter a check. Though it might not make the most sense in this case because we know that changing the RAM provoked the issue, since it's quite easy for me to confirm that the power adapter is good, I might as well rule it out. To do this, I could have used my multimeter to measure the voltage that the adapter outputs under no load, and I also could have used my oscilloscope to measure whether or not the power supply had an unusual amount of ripple in it, but instead I chose to do something different. Because I have adjustable bench power supplies, I found an old barrel jack cable that matched the plug of the adapter that the B-Link uses. I then took that cable and hooked it up to my bench power supply, whose voltage I matched to the AC adapter's voltage and current limit I set to the adapter's rated maximum current. I then double checked that the voltage coming out of the barrel jack cable I had connected to my power supply was correct and that it was the right polarity with my multimeter, and powered the B-Link up using it. The benefit of doing this is that I not only now know that the voltage being fed to the B-Link is clean, but I also get to watch the amount of current that it's drawing when it's booting up. There's a very low chance that this computer has a direct short in it based on the fact that it mostly spins to life, minus the display of course, but the power supply's current readings should confirm this. With the B-Link powered up and doing whatever it was doing, I watched the current measurement on the power supply. I didn't put my camera on it for whatever reason, but the B-Link was drawing about 1 amp from the power supply, which at 12 volts seems like a normal amount of power to draw in startup. Also, the B-Link's AC adapter is rated to do 3 amps, so it was only drawing 1/3 of what the spec'd power adapter can provide, further making this current draw unsuspicious. So, with this now known, I'm confident that the issue resides on the motherboard. I'm not a trained electronics repair technician, and I've not done much regarding motherboards and their inner workings at all. I design and build my own circuits from scratch, but understanding someone else's circuits with no reference materials and figuring out how to fix them is a different beast altogether. In any case, repairing this board is absolutely worth a shot, so I went ahead and tried something that made sense considering the circumstances. Replacing the RAM module obviously requires putting some force on the SODIMM slot, and I wondered whether or not that force might have been the final straw for an already weakened solder joint on the slot. So I proceeded to do my best to refill the RAM slot with my soldering iron and way too much flux. It was an ugly job at best, but I was confident that none of the pins were shorted and that the board shouldn't be in bad shape, though it was quite messy. Sadly though, this reflowing of the SODIMM socket yielded no results, and the system continued to power on but refused to post. At that time, I wasn't sure what to do, and so I moved on to the next computer, which I'm going to get to here soon, but there is more on the B-Link that still needs to be shown. In the following few weeks, I researched a little bit on motherboards and motherboard repair, mostly looking at laptop motherboards because there isn't much repair information on these mini PCs yet, and these mini PC boards are very similar to laptop motherboards. I also managed to acquire some new soldering gear and a microscope for some other projects, but even though the gear doesn't make the difference and instead the person operating it does, I felt a lot more confident about messing with these mini PC boards, so let's take a closer look at the B-Link. I started by figuring out how the main power supplies in the B-Link worked. The 12 volt comes in from the adapter at the barrel jack, and then appears to branch out into these two different DC to DC converters. With the B-Link motherboard out on my bench, I plugged it into power and turned it on. With the B-Link turned on, I used my multimeter to check the voltages on the board. The 12 volts made it into the motherboard, and then it seemed to go into a 5 volt regulator, which was closer to the barrel jack, and after that there was a second converter that was doing 3.3 volts. I then went off on a bit of a tangent with my thought process and tried to reinforce the soldering on the two HDMI ports for some reason. I'll chalk this one up to me just not knowing exactly what to do next, but needless to say, messing with the bad looking solder joints on these HDMI ports wasn't helpful, and the system still didn't post. While trying to post the board after messing with the HDMI port, I left the CPU fan off and felt the heatsink to see whether or not the computer's CPU was getting warm at all. This would indicate whether the CPU was getting power or not, and I mainly decided to gauge whether VCore was present or not through this method, rather than measuring the power phases for a decent reason. The power phases are hard to measure with the heatsink right next to them, and since this is a direct die cooler, I can't power the system up even for a short time with no heatsink on without immediately overheating the CPU. With a CPU that has an IHS, you can power the system on without a heatsink attached for a couple seconds to get some measurements, but you can't easily do that on a direct die cooled CPU. The CPU was getting really quite warm, so it was definitely getting voltage. At this point, I didn't really know what to do with the system as I just didn't understand where to go next. So I decided to pull out the DDR5 SODIMM module and the 500GB NVMe SSD, and at least for now, call the B-Link system a loss. I do have an update on the B-Link system at the end of this video though, because I learned another detail that I originally missed and did some more probing on the board off camera. But before we get to that, let's move on to the other system because we've been working on this B-Link for quite some time now. The other mini PC that Carey gave me is this Zulu XR1 Max mini PC, and this is a pretty darn nice computer. It's got a Ryzen 7 5800U with 8 cores and 16 threads, 16GB of DDR4 RAM, and a 1TB NVMe SSD. I'm really hoping to get this system fixed, as I think it's a pretty awesome little powerhouse of a computer. I'll start out with the Zulu in the same way that I did the B-Link, by going through the standard troubleshooting steps for the issue that it's exhibiting. I connected the Zulu to power and HDMI and hit the power button. The system spun right up and the small OLED screen in the front of it illuminated. I let the system sit for a bit, but it did the exact same thing as the B-Link. It didn't provide any display to the monitor. I know for a fact that the monitor was on, the HDMI cable was good, and that the input was set correctly too, so it's definitely another case of a computer with a power but no post problem. However, this Zulu has that little OLED display which is showing me just how much life this system still has in it. The fan speed percentage and the temperature are both updating, and the values they're outputting are believable, so it's clear that the system is alive and doing something, just not providing a display. I think that the system might be fixable, which is something I'm very glad to see. I went ahead and pulled off the top and back panels of the little computer so that I could pop the main assembly out of the casing. With the computer part of the computer out of its case, we can see that this thing is constructed in a bit of an unconventional way. There are two boards, the main motherboard and an I/O board, which also has the NVMe drive on it. These boards are stacked on top of each other. Then, there are 4 ribbon cables coming up from the I/O board which plug into the motherboard. In the video Carey did on this computer, he mentions how annoying this construction can be, and I totally agree. Working on this system definitely wasn't my favorite repair job ever because man, those ribbon cables are really annoying. In any case, with the motherboard part removed from the rest of the system, I began to inspect it. We've got a single 16GB stick of DDR4 3200MHz RAM in the system, which is actually really convenient. I have some known working DDR4 SODIMM modules in my Lenovo ThinkCentre Tiny, so I can test some known good RAM modules in here to see if it's an issue with either the RAM stick or one of the 2 SODIMM slots. I also quickly took the SODIMM from the Zulu and put it into the Lenovo, which posted using it with no issue, so I can confirm that that RAM stick is good. I'm also going to pretty much skip over the testing of the other RAM in the Zulu and the testing of both the Zulu's slots because it yielded no results and the machine still didn't post, plus I'm sure you all know how to change out a SODIMM module and then power on a computer. I also went ahead and pulled out the CMOS battery, both in the hopes of clearing the CMOS settings and also so that I could give it a test to ensure the voltage is correct. My polarizer made it pretty hard to see, and the reading only popped up for a split second because it was really hard to get good contact with the pins on this CMOS battery, but it measured at 3.04 volts, which is a good voltage. I put the computer back together and tried to post it with the newly reset CMOS, but there was still no display coming out of this PC. I then let a little bit of time pass and did my bit of research on motherboards and repairing them, and now is when things are going to start to get really interesting because this motherboard has a lot of pretty standard looking chips and circuitry. Chips and circuitry I was able to find some general troubleshooting information on. But quickly before I hop over to the microscope and look at this board, I'd like to thank the sponsor of today's video, PCBWay. PCBWay is a company who offers several different high-quality custom manufacturing services. Chances are, if you're someone who enjoys poking around on PCBs and repairing them, you might be interested in creating some PCBs of your own. If that's the case, PCBWay's affordable and high-quality PCB manufacturing service is something that you should absolutely check out. I've been using their PCB manufacturing service for a bunch of my projects, and I've been nothing but pleased with the results. Check out PCBWay and their high-quality manufacturing services at the link in the description. Alright, back to the mini PC. With my new soldering gear and a small bit of newly acquired knowledge, I pulled the Zulu back out and started to do some deeper troubleshooting. I powered it on quickly to ensure that the issue was still persisting, as sometimes computers will do that weird thing where they're broken, you change nothing but putting them on a shelf for a few weeks, pull them out again, and they work just fine. However, this time that wasn't the case, and the system still powered on but wouldn't post. The OLED display was displaying the fan speed and CPU temperatures still, and was also actively updating, which is a good sign for this system's repairability. I went ahead and pulled out the motherboard once more and began inspecting it in detail. One other thing that I allowed myself to do as well was removing the CPU cooler, as the big slab of copper that Zulu used, while a very high quality feeling cooler, covers a lot of the motherboard's probable components. Removing the CPU heatsink reveals a pretty high number of chokes for a mini PC such as this one. All of these chokes are usually associated with different power supply circuits that convert the 19 volts main input into voltages that the internal components can actually use. Just as with the B-Link though, I cannot power on this system to probe all of these chokes with the multimeter. This is because the CPU heatsink has to be off in order to reach these components, and powering on a system like this with the CPU's die entirely bare is a very bad idea. Thankfully, after digging around in my heatsinks for projects box, I pulled out this little one that was previously from a Raspberry Pi high, and it fits this die beautifully. With a little added thermal paste, it sat very nicely on top of the die and allowed me to probe these voltages. Now, this heatsink is not capable of cooling this Ryzen 7 at all, and I'm only using it in short segments of having the system powered on to buy me enough time to get some voltage readings. 19.5 volts was present at the input of the system, and a lot of the voltage rails were off while it wasn't turned on, which isn't surprising. However, one of the green inductors next to the two ribbon cable connectors was outputting about 5 volts, presumably for USB that's powered through the ribbon cables. The other green inductor was seemingly a 3.3 volt rail, which works with a lot of the system, but also likely the NVMe SSD that runs primarily on 3.3 volts. This also explains its positioning next to two more of the board interconnect cables. With the system still off, I was also able to locate the 1.8 volt rail, and a rail that was outputting about 0.76 volts as well. I then hit the system's power button, and with the system powered on, as is evident by the CPU fan spinning, I measured the chokes that should be on the V core rail. It started out on 1.1 volts and then climbed to 1.3 volts, which seems like relatively normal behavior for a Ryzen V core rail during a post. After letting the system cool down for a minute, I powered it on again and checked another choke, which was another 0.76 volt rail. After that, I checked one that was located very close to the RAM slot, assuming it would be 1.2 volts for the DDR4 memory, which it was. At this point, I was relatively confident that the voltages across the board were all good and that we had no power issues. At least not at the power supply parts. Now, where should I go from here? Well, I found this video from the YouTube channel LapFix, which goes over some basic laptop motherboard troubleshooting, and this video has been immensely helpful, so check it out at the link in the description. In short, the video said to check voltages, and if those are good, we can check what's called the startup chip, which is also known as the Super I/O chip. The important thing to check for here is that the Super I/O chip is getting power, which should be 3.3 volts, and this can generally be checked by just probing a few of the capacitors around it, which is what I did. I replaced the CPU's heatsink and fan assembly, and powered on the system while checking some voltages on the Super I/O chip's capacitors. We were getting 3.3 volts on most of them, and not all of the capacitors are between 3.3 volts and ground, so it's very likely that the power to this chip was fine. While I was probing around this area, I discovered something that looked unusual and would prove to be a very crucial part of this repair. An area that looked like it had either been blown partially or been hand soldered and had some old flux left behind. Here you can see the spot that I saw and needed to troubleshoot. There was a capacitor and a resistor right next to each other, and it looked as if the resistor had either gotten really hot or been hand soldered. I wasn't sure yet, but whatever was going on here didn't seem quite right. I did my best to measure the resistance of the resistor while it was in the circuit, which never yields highly accurate results because the resistance measurement will catch other things on the board than this resistor, but I wanted to see if I could find any place to start from. Finding schematics for this computer was never going to happen, so I had to do my best to reverse engineer from what I've got here, which looked almost like a failed resistor. I didn't get a shot of it, but the resistance measurement on my multimeter did some weird things while measuring this resistor. It would constantly switch between OL, something random in the mega ohms range, and then about 9.3 kilo ohms. So I decided to desolder this resistor, clean up the area around it with some alcohol, and lastly replace it with a 10 kilo ohm resistor as a starting point. Some isopropyl cleaned up the spot nicely, so it didn't seem like anything had burned, and it was just old flux that was giving the area that burned color. With the old resistor removed, I had to find a way to get the temporary replacement into the circuit. I don't have SMD resistors on hand yet, I've got some coming now, but at this time, all I had were quarter watt through-hole resistors, which are not quite the right size as you can see. But nevertheless, I managed to find a way to make the 10K resistor fit onto the motherboard in a way that it could still be attached to the case. This resistor was never going to be a permanent solution and was just a quick value test to see if 10K was right or not. If this resistor worked, I'd order the right part and install that at a later time. Now that the 10K resistor was installed and the system was partially reassembled, I plugged in power and hit the power button. The fan twitched and then nothing else happened. Holding the power button down kept the fan spinning though. It almost seemed like the circuit that I had been messing with was some kind of latch with the power state from the power button, and 10K was too high a resistance to hit the switch and have the on state latch into place. And I use air quotes here because this is almost certainly not quite what's happening, but you can probably see what I mean and where I'm coming from. I then decided to try and measure the resistance of the resistor that I had removed from the board, and it measured at 0.2 ohms. quite odd. I was also certain that this wasn't the metal bed of the microscope, by the way, as it's powder coated and the multimeter read it as OL when directly measuring it, so it's not a short from the bed of the microscope. Alright, so clearly 10K is too high and 0.2 from that resistor seems to have some issues. So how about a value a lot lower than 10K, something more like 1K? I went through the same install process as I did with the 10K resistor, but this time with a 1K resistor, and it exhibited similar behavior to what the 10K resistor did. I'll also quickly mention here that I measured the resistance between the pads of this resistor we're dealing with and the power button's terminals. They were connected, though through two very high resistance pathways, one about 500 kiloohms and the other about 36 kiloohms. As a small experiment, I decided to try out shorting the pads of the resistor altogether with some solder. It could have been possible that the 0.2 ohm tiny resistor was good, but the solder joints or the old flux was causing it the issues. I shorted the resistor's pads, or what was left of them because I broke one of them off, and tried powering on the system. I was not ready for what was about to happen, as is evident by the camera being solely framed on the PC and not the monitor at all. But after pressing the power button and waiting a few seconds with this solder bridge, the mini PC posted for the first time, at least in my hands. It also went ahead and booted into the Windows 11 install that had been on it when Carey last used it, so I was quite confident that this little computer was fixed. I won't spoil it too much here, but as I was messing with this PC later, I noticed that it has another issue that needs to be addressed. That will be a follow-up video because this one is already absurdly long. I'm on page 10 of this script. This is insane. In any case, at least one issue with the Zulu has been fixed, and soon I'll have another video working on the other issue, which is storage related. Now, if you're still here, I've got to say that that is awesome. Listening to me ramble for this long straight is impressive. But earlier, I said that I had an update on the B-Link, so I'll just let live audio me take it from here on that. Alright, so it's been a little bit since I first started working on this B-Link, and after doing the stuff on the Zulu, I decided to come back to this after talking a little bit with Carey about what exactly broke this. So I originally thought it had broken just after a regular RAM swap, just taking out the old RAM and putting the new RAM in. However, it turns out that there's actually more to it than that. The thing that most likely caused it to be broken by that procedure was the fact that Carey left it plugged in while he did the RAM swap. So that explains the fact that the RAM swap kind of messed it up. It makes it a lot more reasonable. Originally, I was thinking that just the force of inserting and removing the RAM might have messed up the socket, which is why my first instinct was, hey, let's reflow some of these pins, see if it broke a faulty solder joint, but that was not the case. And I don't feel like I did the most thorough job at diagnosing this past that because I just wasn't sure where to go. But I ended up picking it up again off camera and messing with it for a couple hours. I'm not gonna go all the way through everything that I did and found out, but I want to update and talk a little more about this because I now have a theory on what went wrong with the system and what's broken on it right now. Sadly, the thing that's broken is something that I don't think I can replace. It's definitely something that is not worthwhile to replace, but I want to go through my thought process because I want to know what some of you think. I'm certain some of you are much more advanced electrical technicians than I am, and I'd like to hear your thoughts on what I have theorized based on my findings with this motherboard. I still don't have any RAM in here, mainly because I think that this computer is going to end up being a lost cause. At least my theory definitely puts it in that category. But then again, my theory could always be wrong. So we're gonna find out. That's why we're gonna hang on to this guy for a while. So this board is kind of an interesting board. It doesn't have a massive, big old, giant ITE startup chip like the Zulu one did, but it does have one, and it's just kind of hidden away right here underneath the CMOS battery. So I located that, and I messed around a bit on that. I found a component that looked a little weird. I actually found a schematic for kind of the application here of this exact startup chip. And I located that component, and it was basically just another 0 ohm resistor, at least I believe. So I tried jumping the contact with solder, but that didn't change anything. The main thing that I did was I actually went and I measured the voltage on all 4 of these power stages. So I originally thought that, these are probably all 4 for the CPU, which arguably doesn't make the most sense because the N100 in here is a very low powered CPU. It probably doesn't need 4 power stages. In any case, I didn't really check all of them. I just assumed that number 1, they were all for the CPU, and number 2, that they were all functional because of how warm the CPU got. This CPU was putting out a reasonable amount of heat, so it was very much alive and active, doing something. Again, it was clearly getting power, so I wasn't too concerned about the V-core stages. However, I went ahead and I measured the output voltage of all of these. This one right here doesn't seem to be related to CPU power much at all. It might power something on the CPU, but this just seems to be the system's kind of board-wide 1.8 volt rail. Very common rail. The Zulu had it. I know a lot of graphics cards have 1.8 volts on them. So this phase right here was kind of just the 1.8 volt rail. And then these 2 phases right here, these 2 guys right here, are both working together to produce about 0.85 volts, which I believe to be V-core. They are connected together. The resistance from the output to ground is about 15 ohms, and they're producing about 0.85 volts when the system is on and just not displaying. So I'm pretty confident these are V-core. The N100 runs at a very low clock speed, and it's an Alder Lake chip, which is a relatively efficient architecture, so it doesn't need tons of voltage. It's not quite efficient as some others. So 0.85 volts to get the clock speeds the N100 is doing on the 4 cores that the N100 has. I think it's 4 cores. Anyway, 0.85 volts, it's got to be V-core. I'm pretty confident of that. Plus, it's the only voltage that had 2 phases dedicated to making it, working together on that, so clearly I think V-core. And then there's this one down here, which is a little bit different. This one's actually got its driver circuitry right next to the MOSFET. These 2 have the driver circuitry on the back of this board. This one is a little bit of a different phase here, and this one was not outputting any voltage at all. Straight 0 volts. I thought that was very, very weird. I thought that this might be the reason that we weren't working, that it just wasn't functioning, the reason that it wouldn't post. However, I think this power stage is actually working fine, and I'll get into that a little more in just a second. By the way, I hope this audio is going to be okay. I've tried something different. Rather than using my cheap lav mic, I've got a overhead boomed small diaphragm condenser. But yeah, this phase wasn't outputting any power at all. And so I traced the circuitry for these 3 phases, because this one's entirely separate. This guy's doing its own thing. This is just the 1.8 volt rail. These 3, I traced them back through their drivers all the way over here to, that's as much zoom as I've got, this chip right here. This chip is our main power control chip. This controls the VRMs for the CPU and such. And over here you can see the 2 driver circuits for the 2 phases that power V-core. And then we've got this guy and some bigger capacitors on the undersides of the phases. But this right here, this chip, I looked up the model number. Let me see what it is again. It is an RT3624BE. And I looked up that number and I found on the manufacturer's website, I believe it was the manufacturer's website, I found some data on the chip and I discovered something very interesting. This supports 2 different voltage rails on its output. So it's got, it can support up to 4 phases on one rail and 2 phases on another. And so I did some digging with these pins and a multimeter and these driver circuits, and I found out that the 2 phases that I suspect to be V-core were connected to 2 of the phase outputs on the main rail that this supports, and then the other one was connected to the other rail, the auxiliary rail. And after doing a little more research, just looking up some stuff, trying to find out what was going on here, why there was a separate phase that's doing its own thing, I discovered that separate phase is likely to be VAXG. I think it's AXG. VAXG is the integrated graphics voltage. And VAXG, again, I'm just presuming it's VAXG based on the stuff I was able to find, is gone. So we're not going to get any video because we don't have any integrated graphics. Hence, the power but no video makes a lot of sense now. Alright, I thought, so something's gone wrong with one of our power rails. So we're not getting power to the integrated graphics, and therefore we're not getting any video out. And here's the thing with that theory. I don't know if that would make any sense, because switching out the RAM while the system's powered on can cause a myriad of issues. Or sorry, not powered on, plugged in. But killing our integrated graphics power phase is not one that I would immediately expect. It just doesn't make sense. How does changing your RAM out while the system's plugged into power kill the phase that controls the graphics power? That just doesn't make sense. So I actually think that the phases are working fine. Plus, another thing, I probed the output, I probed the gate signal and the outputs from the controller. And these two, for the V-Core, we're getting about a 650 kilohertz signal with about a 90% positive duty cycle on their gates. I don't know if these are N-channel or P-channel MOSFETs. I'd assume they're N-channel because that's generally more efficient. So I'd assume these are running at about 90% duty cycle. And then on the output of the controller was a 10-ish% positive duty cycle. So these drivers are clearly inverting drivers. They invert the signal from the controller, and they send it to the MOSFETs as an inverted signal. When I probed the output of the controller for this rail, I discovered that it was pinned to 100% positive. Hence, this MOSFET was getting a 0% positive duty cycle, meaning that it should be entirely off. And actually that means that these are N-channel, because if the voltage is low on the gate, it should be off, which it was because we weren't getting any voltage. So it's clear that the control chip isn't even trying to tell that power phase to do anything. In fact, it's telling the power phase to not do anything. And I think that seems to be a conscious command from this controller. I think that this controller is not being told to turn on the iGPU's voltage rail. And this is where my theory starts to get more uncertain for me personally. I'm not very experienced with the exact way that post works in these computers. I'm not sure exactly about the order, but I have some ideas, and I'm just going to share them here. I could be wrong, so let me know what you think if you think you know what it actually is. I think the post in these computers, when we turn it on and it starts testing things, I think that it tests the CPU first. So we have V-Core, of course, so that we can test the CPU. And once we test the CPU, I would assume we move on to system memory after the CPU, because, I mean, it's one of the key components. It should be one of the next logical steps. And then after memory, I think then we move on to the iGPU. I'm pretty sure that there's other things thrown in there along the way, but the important thing is I think it goes CPU, memory, iGPU, and I think the memory is failing. I think the memory is failing the post-test, and therefore the BIOS is not telling our startup chip, or Super I/O chip if you want to call it that, to turn on through this controller the rail that's providing voltage to the iGPU, and so we never get any video. The best explanation I have for why the memory would be failing is I think that when the RAM was switched out with power engaged, I think that the memory controller on the CPU got killed. So I think the memory controller on the CPU is gone, and because of that, I think we're not making it past memory checks. In fact, actually, now that I'm talking about it, we might not even be making it past CPU checks. So now that I've kind of explained that, that's my main theory. I think that when the RAM was switched out with power on, I think the CPU's memory controller got killed. And when we boot the computer, it runs its post tests, and either the CPU or the memory, I think it's more likely that it would catch it during the memory tests, is failing. And because of the fact that the iGPU relies so heavily on system memory to work, I would expect that we test the iGPU after CPU and memory pass. If one of those fails, I don't think we ever get to the point where we test the iGPU. I think the post hangs there. Again, I'm not 100% sure on that, but I think that's what's happening. And because the post is hanging there, I think that the Super I/O chip here is never telling our power chip here to turn on the phase for the iGPU, because the Super I/O chip on this board does seem to handle some things regarding power and power phasing, and I believe that it talks to the VRM controller. And therefore, I think that the B-Link is dead because of a dead CPU. And number one, I am not skilled enough at SMD soldering, and really this would be hot air rework soldering, to solder a new CPU onto this board. And number two, the only replacement N100 chip that I could find was $225, and a new one of these systems with 16 gigs of DDR5 and a 500 gig SSD costs $250 on Amazon. So I think that this system is, as sad as it is, a goner. I don't think that there's anything left that can be done about this system. I don't think we can fix it. Again, if you think that my theory is wrong and have another thing for me to try, I will happily give it a shot. Because, I mean, why not? We don't really have anything to lose. It's already broken. Might as well try. But I think I'm relatively confident in that theory being at least mostly correct. And because of that, I don't think that this board will be coming back, because replacing the CPU is just not economical at all. But yeah, that is the update that I have on the B-Link. I played around with it for a while, just discovered some things. I didn't bring the camera out because I didn't feel like filming at that time of night, and I didn't think I'd get it fixed anyway, and I didn't. But I just wanted to put that in here because I feel like originally I didn't do the most thorough job at working on the B-Link, and I changed that. I've now really messed with this board a lot, and I've learned a lot more about how the power stuff works and the interface of the Super I/O chip. So I think the CPU's dead. Well, that's all that I have for you today. One more thanks to PCBWay for sponsoring this video, and one more thanks to Carey for sending out these PCs. I had a lot of fun with them. In any case, I hope to see you next time. Goodbye.